Hello. Today we are going to start taking a look at circular motion, things just going around and around in a circle, but it's quite surprising the number of applications that exist, whether it's a car on the road or a satellite orbiting the Earth. Those things can be understood very well using the principles behind circular motion. We're going to start by examining what we call uniform circular motion. The Canadian Mountie uniform is in a circle and it's moving in a circle. What do we mean by uniform circular motion? The word uniform means it's going around at a constant speed. And then, of course, circular motion means going around at a constant speed in a circle. So one of the consequences of that is that because you're always going around in a circle, your direction is always changing. So even though the speed is constant, the velocity is not constant. So keep that in mind. It means that there's an acceleration. Whoa, it means that there's an acceleration? What is that acceleration? If you're going around in a circle, and this is true whether or not you're going around at a constant speed. If you're going around in a circle, you are affected by a type of acceleration called centripetal acceleration. And we can always calculate centripetal acceleration as being equal to v squared over r, where v is the speed, and r is the radius of the circle around which you're traveling. Notice that the centripetal acceleration increases with the speed v. In fact, it really increases with the speed v because it goes as v squared, but it decreases with r. As r goes up, the centripetal acceleration goes down. And you might be able to apply this idea to your personal experience. If you've been in a car going around a gentle curve, even if you've been going very fast, you're not going to feel like you're being pushed towards one side of the car or the other. On the other hand, you have undoubtedly experienced a situation of going around a cloverleaf, either to get onto a highway or to get off of a highway. And as you go around that cloverleaf, the radius of the circle is actually pretty small. R being in the denominator, being small, means that the centripetal acceleration is relatively large. And you feel yourself being kind of pushed towards one side of the car or the other as you go around this circle. And the faster you go around that circle, the greater that feeling of being pushed towards one side or the other. Well, if v goes up and r goes down, then the centripetal acceleration really increases, and that's the situation in which you feel like you're being pushed towards one side of the car or the other. Now, take that formula v squared over r and apply it to this question right here. We have two objects undergoing uniform circular motion. However, the circle on the right, the circular path on the right, has twice the radius of the circular path on the left. Both objects complete their circular paths in the same period of time, meaning that the speed of the object on the right is twice the speed of the object on the left. Given that setup, which of these objects experiences the centripetal acceleration with the greatest magnitude? The one on the left, the one on the right? Do you think that both accelerations are equal, or have I failed to give you some important information? Think about it. Don't hesitate to ask a question at the start of class if you're not certain about the answer. Now, acceleration, as we have stated time and time again, is a vector quantity, meaning it has both a magnitude and a direction. The magnitude is v squared over r. What's the direction? And the answer is towards the center of the circle. No matter where the object is in that circular path, if I were to draw an arrow representing the centripetal acceleration. That arrow would always extend from the object towards the center of the circle. Any object undergoing circular motion has centripetal acceleration. Undergoing constant speed, you got centripetal acceleration directed towards the circle. If you're speeding up or slowing down, a component of your acceleration is centripetal directed towards the center of the circle. We'll get a little bit more into that later this lecture. But there is always centripetal acceleration if you're going around in a circle, not just at constant speed, but just as long as you're moving around the circular path. Speeding up, slowing down, don't care. If you're going around a circular path, you have centripetal acceleration at least as a component of your overall acceleration. We need to start taking a look at units associated with circular motion. It might be tempting to use meters and meters per second and meters per second squared, and we'll see that. For instance, centripetal acceleration has units of meters per second squared. There's nothing special about that part of it. But we are also going to look at circular motion from the perspective of how the angle is changing over time. And so we need to understand the variables that allow us to measure the angular motion. First off, angular displacement. We need to have a reference. We typically use the positive x-axis as representing 0 degrees. And then we can extend counterclockwise. We can subtend an angle counterclockwise that allows us to connect up to where the object is along the circle. As you can see on the screen, theta represents the angle subtended from the x-axis to the line connecting the object to the center of the circle. This would be the angular displacement of this black circle. Sadly, we don't use degrees as the standard unit in angular motion. Instead, we use the unit known as the radian. The conversion factor from degrees to radians, 360 degrees is a full circle. Equivalently, 2 pi radians is a full circle. So our conversion factor would be 360 degrees equals 2 pi radians. Where did that 2 pi come from? Why such a crazy value? And the answer comes from the formula for the circumference of a circle in terms of radius. If you know the radius, the circumference is equal to 2 pi r. Now, another way of looking at it is if you go completely around the circumference of a circle with radius r, you have not only traveled a distance of 2 pi r, you've undergone an angular motion of 2 pi radians. Why is that useful? What's so special? And the answer is it allows us to very quickly calculate arc length. Arc length is the distance along the circular path traveled by the object relative to the origin, which is along the positive x-axis. I shouldn't say the origin, relative to where the positive x-axis intersects the circular path. Arc length is often represented by lowercase s, letter S as you see towards the bottom of the screen. And if I measure my theta in radians, then it turns out that the arc length s is simply equal to the radius of the circle times theta measured in radians. So it gives us a very, very quick way of determining the arc length. Let's take a look at an example. We are going to determine both the speed and the centripetal acceleration of a bug on a spinning disk. The disk has a diameter of 22 centimeters, and the bug is right on the rim of the disk. And the bug and the disk travel through an angular displacement of 73.0 degrees in just 0.830 seconds. We want to find the speed. We want to find the centripetal acceleration. To do this problem, we need to first find the radians. 73 degrees, we multiply by 2 pi, and we divide by 360 to get the number of radians. In this case, 1.274 radians. Now, to put this into context, 1 radian is almost 60 degrees. So 73 degrees being a little bit more than 60, 73 degrees ought to be a little bit more than 1 radian. So 1.274 radians seems reasonable. Next up, don't fall into this trap. You want the radius. You are given the diameter. Don't forget to take the diameter and divide it by 2 to get the radius. So the diameter of 22 centimeters is equivalent to 0.22 meters. You divide that by 2, and the radius becomes 0.11 meters. Now, the bug travels through an angular displacement of 73 degrees at a radius of 0.110 meters. What is the actual distance it travels? Thanks to knowing the displacement in radians, this is a quick calculation. R is 0.11, theta is 1.274. The physical distance the bug travels is 0.140 meters. Quick, quick, quick. The speed is equal to the total distance divided by time. The bug travels 0.140 meters in 0.830 seconds. We divide, and we find that the speed is 0.169 meters per second. This speed is exactly how fast it's going around the circle. The speed is not changing. We can find the centripetal acceleration by using v equals 0.169, r equals 0.11, and I calculate the centripetal acceleration, v squared over r, to be 0.260 meters per second squared. That gives us the magnitude of the centripetal acceleration, and of course the direction is towards the center of the circular path, which happens to be the center of the disk. So, if we have angular displacement, do we have angular velocity? Yes. And by comparison, regular velocity, linear velocity, whatever you want to call it, how fast and in what direction, that's equal to the change in displacement over time. And yeah, I used r instead of x, big whoop. Change in displacement over time is velocity. Well, change in angular displacement over time is angular velocity. So change in displacement over time, velocity. Change in angular displacement over time, angular velocity. Angular velocity denoted by that curly W, which is actually the lowercase Greek letter omega. You're going to hear me refer to it as omega, not W. Be very careful. Now, we saw the angle represented with a vector symbol, and that can lead to an uncomfortable and confusing conversation. I don't want you to worry about that. The vector symbol just reminds you that displacement, whether it's regular displacement or angular displacement, is a signed quantity. In circular motion, counterclockwise is the positive direction, clockwise is the negative direction. So in the little graphics at the bottom of the screen on the lower left, we see an example of positive angular displacement, and in the lower right, we see an example of negative angular displacement. So counterclockwise, positive, clockwise, negative. You can read the stuff that I've overwritten with a dashed line, with a solid line. It's not that important. Counterclockwise is positive, clockwise is negative. Take a look at these two examples of angular velocity in action. Note that the Ray Charles CD on the left is rotating clockwise and relatively slowly. The angular velocity is small and negative. The same Ray Charles CD on the right is rotating counterclockwise and relatively rapidly. The counterclockwise motion means it's positive, and the angular velocity is relatively large in magnitude. So angular velocity on the left is negative, angular velocity on the right is positive. Here's a conceptual question to hopefully make sure that you are following along with these concepts. We have two bugs on a disc. One of them is at the outer edge, and it's a little merry-go-round like on a playground. One of them is at the outer edge. One of them is halfway from the very center and the outer edge. And they both stay fixed on the disc, but the disc itself is going around in a circle, and the bugs remaining fixed on the disc are therefore going around in a circle, each of them. What can we say about the gentleman bug, which is the inner bug? What can we say about the angular velocity of the gentleman bug compared to the angular velocity of the ladybug on the outer edge? Is the gentleman bug's angular velocity half the ladybug's? Is it the same as the ladybug's? Is it twice the ladybug's? Or have I not included some significant information? Think about it. Again, don't hesitate to ask at the start of class if you're not certain. There's angular displacement. There's angular velocity. Is there angular acceleration? Yeah. Linear acceleration depends upon change in velocity over time. Angular acceleration depends upon change in angular velocity over time. The symbol for angular acceleration is the lowercase Greek letter alpha. That's that kind of curly, slightly warped fish symbol that you see here on the lower right. Alpha equals delta omega over time. Angular acceleration is a signed quantity. It can be positive, it can be negative, and the determination of whether the angular velocity is positive or negative follows the same logic as determining whether the linear or regular velocity is positive or negative. Remember, if the object is speeding up, the velocity and the acceleration have the same direction. And if the object is slowing down, the velocity and the acceleration are in opposite directions. This idea applies exactly to the angular variables. If the rotation is speeding up, the angular acceleration has the same sign as the angular velocity. If the rotation is slowing down, the angular acceleration has opposite the sign of the angular velocity. Oops. Bear in mind, uniform circular motion. Uniform means the speed stays constant. If the speed stays constant as it goes around a circle, angular velocity stays constant. If angular velocity stays constant, the angular acceleration is zero. But don't confuse angular acceleration with centripetal acceleration. If you are traveling around in a circle, you have centripetal acceleration. But you would only have angular acceleration if you were speeding up or slowing down. Couple of cheap graphics on the screen. We see a fan blade on the left, and we see that at the beginning of the animation, it starts to rotate clockwise and then it speeds up. On the right, we see a tire, and at the beginning of the animation, it's rotating relatively quickly and it slows down. But notice that the tire is rotating in a counterclockwise direction, the fan blade's in a clockwise direction. If the fan blade is speeding up, as it is, the angular acceleration has the same sign as the angular velocity. Since it's moving clockwise, the angular velocity is negative. Since it's speeding up and moving clockwise, the angular acceleration is negative. But on the other side, it's initially rotating counterclockwise rapidly and it slows down. So its angular velocity is positive. Its slowing down means that the angular acceleration has the opposite sign. So in each of these cases, the angular acceleration is negative. Units: angular displacement in radians, angular velocity in radians per second, angular acceleration in radians per second squared. It parallels linear variables, except instead of meters, we have radians. And the parallel continues with our equations. In one-dimensional kinematics, we can talk about x final equals x initial plus v initial t plus 1/2 at squared. We have a corresponding equation with angular variables. Theta final equals theta initial plus omega initial t plus 1/2 alpha t squared. V final equals v initial plus at, the angular counterpart. Omega final equals omega initial plus alpha t. V final squared equals v initial squared plus 2a x final minus x initial. Omega final squared equals omega initial squared plus 2 alpha theta final minus theta initial. Lots and lots of parallels between linear motion and circular motion. Let's do an example. We have a ceiling fan that starts at rest but gets to an angular velocity of 35 radians per second in 7.3 seconds. Now read the question carefully. I bold-face one of the words. Through how many revolutions does the ceiling fan turn before reaching final speed? We'll work to the idea of revolutions, but let's first find the radians. We have 6 different variables. When in doubt, theta initial is 0, just like when in doubt, x initial is 0. Theta final, that's something that we want to find. The fact that it starts from rest tells me that omega initial is 0, and then we're told the final angular velocity is 35 radians per second over a time of 7.3 seconds, with alpha, the angular acceleration, also being unknown. Of the 6 variables, we know 4 of them. We can proceed. And we'll start by using omega final equals omega initial plus alpha t. Alpha is an unknown quantity. This first equation, alpha is the only unknown quantity. We're going to solve for it. And the procedure is just like with one-dimensional kinematics. We do final angular velocity minus initial angular velocity, and then we divide by 7.3 seconds. And I calculated the angular acceleration to be 4.79 radians per second squared. Is it positive or is it negative? I don't know. The problem doesn't say anything about the direction in which the ceiling fan is rotating, so we're just going to keep it simple. Now that I know alpha, I can solve for the final unknown, theta final. And I plug into the equation, and I get that theta final is 127.75 radians. Now that's the angular displacement at the end of 7.3 seconds, but that is not what the question asked. The question asked for the number of revolutions. A revolution is a full rotation, and a full rotation, like in any full circle, corresponds to 2 pi radians. So if I want the number of revolutions, I have to take the number of radians and divide by 2 pi. 1 revolution is equivalent to 2 pi radians. So if I start with radians, I divide by 2 pi, I get the number of revolutions, and in this case, I get 20.3 revolutions. Hopefully, this answer makes some sense. Again, ask me questions. I'm happy to help. Now, the next topic is, in a way, it's a bit more relevant to your day-to-day life. If you're driving in your car and you're going around a circle, you look at your speedometer, it's not going to tell you your angular velocity, it's going to tell you your speed. But in the context of going around in a circle, we can say that it is going to tell you your tangential velocity. There are so-called tangential variables that are exactly partnered up with each of the angular variables. So there is an angular displacement, there's a tangential displacement, an angular velocity, a tangential velocity, an angular acceleration, a tangential acceleration. Tangential variables are measured the same way as linear variables. Tangential displacement is the number of meters. Tangential velocity, meters per second. Tangential acceleration, meters per second squared. And the relationship between the tangential variable and the corresponding angular variable is a factor of r, the radius of the circle. The tangential displacement is equal to r times theta. The tangential velocity is equal to r times omega. The tangential acceleration is equal to r times alpha. Theta, omega, alpha, measured with units of radians, but tangential variables are measured using meters. So theta, omega, alpha using radians, xt, vt, at using meters. Meters, meters per second squared. When you look at your speedometer, you're seeing your tangential velocity. Again, a reminder, uniform circular motion means you're not speeding up. It means that your tangential velocity is staying constant. That means your tangential acceleration and your angular acceleration are both zero. Tangential variables have signs that exactly match with the angular variables. If the tangential variable extends clockwise, it is negative. If the tangential variable extends counterclockwise, it is positive. This is true for when it's moving, if we're talking about tangential velocity. The object on the left, the red one, is going around a circle counterclockwise, so it has a positive angular velocity and a positive tangential velocity. The blue circle on the right is going around the circle clockwise, so it has a negative angular velocity and it has a negative tangential velocity. The direction of the tangential acceleration exactly matches up with the direction of the angular acceleration. So, is the object speeding up or slowing down? If it's speeding up, the tangential and the angular have the same sign. The tangential and angular acceleration have the same sign as the tangential and angular velocity. If the rotation is slowing down, the acceleration, both tangential and angular, have the opposite sign. The tangential acceleration, the reason it's called tangential, and I should stress this, we saw it in the previous graphic with the objects going around the circle. The arrow representing that variable is always pointing tangentially to the circle. So I could conceive of, in the lower left with the red circle, perhaps the tangential acceleration is this red arrow pointing to the lower right. But just because it's pointing to the lower right does not mean it's negative. The fact is this arrow is indicating a counterclockwise trend. If the trend is counterclockwise, it's positive. For the blue spot, the arrow is pointing to the upper right, but that doesn't mean anything in terms of x variables and y variables, ignore that. In circular motion, does it have a clockwise trend or a counterclockwise trend? And for the blue, the trend is clockwise. It's like it's trying to be pulled in the clockwise direction. That means it's negative. Counterclockwise positive, clockwise negative. Now, I said at the beginning that we would always have centripetal acceleration in circular motion. We don't always have tangential acceleration in circular motion. Centripetal acceleration exists as long as A, you're moving, and B, you're following a circular path. But tangential acceleration exists if A, you're moving, B, you're following a circular path, and C, you're speeding up or slowing down. Your speed has to change for there to be tangential acceleration in circular motion. But as long as you have circular motion, you will always have centripetal acceleration. So don't confuse the two. I've talked about three different kinds of acceleration: centripetal acceleration, angular acceleration, tangential acceleration. The latter two, angular acceleration and tangential acceleration, are both closely allied. They both have the same sign. But centripetal acceleration is always directed towards the center of the circle, and it always exists as long as you're moving in a circular path. Where we have tangential acceleration, it is always directed tangentially towards the circle, relative to the circle. If you have both simultaneously, well, there's a drawing. The black spot going around the circle, we have tangential acceleration represented by the blue arrow. It's pointing tangentially to the circular arc. And the red arrow representing the centripetal acceleration, it points directly towards the center of the circular path. The thing that is tangential is always perpendicular to the thing that is radial, R-A-D-I-A-L. The centripetal acceleration directed along towards the center. It is directed along a radius. We say it is radial. Tangential is always perpendicular to radial. And that's it. That's our introduction to circular motion. Bye-bye.